All right, solutes that have the ability to dissolve in a specific solvent are called soluble substances. That means they can dissolve in the solvent. Then we have ones that don't dissolve, and those are called insoluble substances. Now, these are not absolute things, that there are varying degrees to which things are soluble. For example, alcohol is completely soluble in water. Oil, however, is insoluble in water. Now, there isn't any solute that will dissolve in all solvents, and there isn't any solvent that will dissolve all substances. However, water is called the universal solvent because it dissolves many substances. It is polar, and a lot of other substances have basic polar properties to them, and things will dissolve. A lot of things dissolve in water. Okay, which brings us to the types of solutions we have. There are solid solutions, mixtures with a solid as a solvent. So, for example, gas in a solid. If you have a charcoal filter that you use to filter your water through, or it's primarily used for water, but there are other things that charcoal filters are used for. That's a gas dissolved in the carbon. There's liquid in a solid. For example, mercury is in silver for certain dental fillings, and that affects the rate at which the solid expands, so that when you eat something cold, it doesn't contract in your mouth and hurt your tooth, or it doesn't expand in your tooth and hurt it. And then there are solids in a solid. So most metal alloys are this kind. So, for example, sterling silver is copper and silver, and in alloys, our solutions are of two or more metals. For example, 14 karat gold, stainless steel, bronze, that sort of thing. Then there are gaseous solutions. And gaseous solutions are when the solvent itself is a gas, and, for example, air is one of them. Now, nitrogen is a solvent in air. Be? Why would nitrogen be the solvent in air? And it's because it is the most abundant. It is the most abundant gas in the air. Then we have liquid solutions, where the solvent is a liquid, and this is the most frequent kind of solution that we're going to be dealing with. Okay, now liquid solutions, you can have a gas and a liquid, so like any kind of soda has CO2 dissolved in it. Or you can have liquid in a liquid. For example, antifreeze, ethylene glycol, does dissolve in water. This, by the way, is nasty stuff. It is a biocide, which means it kills life. Okay, it kills life, and essentially it's a uh, poison for anything that uses glucose uh, as an energy source. All right. Uh, Other example of these solutions. Okay, we have miscible liquids, and if things are miscible, then they can dissolve in each other in all ratios. So, for example, alcohol and water can dissolve in each other at, to any degree. In fact, um, sort of what the idea of proof of alcohol is based on. There are certain alcoholic beverages that rate their strength based on their proof. And if it is zero proof, it means that there's 0% alcohol, alcohol dissolved in the water. Most hard liquors are about uh, 80 proof. They are 80 proof. Let's write this correctly, Mr. Allen. 80 proof. And that is about 40% alcohol. Okay? Or it is a 3-to-2 ratio of H2O to alcohol. There's over-the-counter stuff here in California. The highest over-the-counter is 151 proof, which is 75.5%, about 75% alcohol. Other states offer uh, grain alcohol, and it's hardcore stuff. It's, you may have heard it's called Everclear, and it is 180 proof alcohol, which is a 90% solution. And then you can mix alcohol all the way up to the 100%. So it is completely miscible with each other, that in any proportion you can have. So down in this range over here, you have water is your solvent. But as soon as you get higher than 50% alcohol, the alcohol is the solvent, and the water becomes the solute. All right, so those are miscible liquids. Then there are other versions which are immiscible, and that these are liquids that do not dissolve in each other in any way. For example, oil and water are completely immiscible. They will separate each other every single time. And then we can have solids in a liquid. So, for example, Kool-Aid or the sugar and flavoring in the water is actually a solid that is dissolved in the liquid. All right, and this brings us to aqueous solutions. This is any kind of solution where water is the solvent. Okay, into aqueous solutions, generally we have electrolytes. These are substances whose aqueous solution will conduct electricity. Okay, and these are solutions with ions. They're charged particles that will go back and forth, and uh, they will actually conduct electricity. So they will the ions themselves will travel through the liquid and create an electric current when they are charged. Okay, and those include salts, acids, and bases. And this is one of the reasons why you drink Gatorade, is because they have these salt, acids, and bases dissolved in the Gatorade in order to replenish your electrolytes that you lose when you sweat. Now, non-electrolytes are solutions that don't conduct electricity. There's no ions. They are molecular in nature, and they include substances like sugars and oils and many organic compounds. So let's talk for a second about Gatorade, because that's a lot of students, or power drinks in general. Okay, Gatorade, or actually Gatorade, but by Gatorade I mean really any sports drink, but in particular the powdered one. Powdered. So where you can mix your own Gatorade. Um, has in it all kinds of stuff. It has sugars, it has glucose, fructose. Okay, fructose is generally your table sugar. Okay, and it equals two glucoses. Glucoses minus one H2O minus the water. So it takes a molecule of water to separate the fructose into two glucoses. But it also contains uh, potassium chloride, and it contains sodium chloride, as a couple of salts also, as well as some potassium chlorides and some phosphates also. Phosphates. Now, these two up here are sugars, okay, and they do dissolve in water, but they stay in their molecular form as glucose and fructose. These guys down here are salts or acids, and these will separate into their potassium, chlorides, sodium, phosphates, and these help your body. These are the electrolytes that you lose when you sweat. And if you've ever tasted sweat before, I know you all have. You've all sweated, and some of it has gone into your mouth. That these electrolytes are the saltiness that you taste in your sweat, and you don't get that back in unless you replenish your system with the electrolytes. Um, and this is what allows your cells to work. When, in your muscles in particular, you have these potassium sodium channels that go inside and out of the cell. And if you start running out of potassium and potassium and sodium in your cells, your muscles stop working. That's when you start cramping. And so that's why you start cramping. start cramping when you lose your electrolytes and must replenish. Okay, and with that you drink Gatorade. Or the other thing that's frequent is you eat bananas, because bananas also provide the potassium for the potassium sodium channel, and those also help prevent the cramping. So that's a little diatribe on Gatorade and why we drink sports drinks and why they actually do help, and that they were developed in order to replenish the fluids uh, for athletes. And long story is actually that Gatorade was invented at the University of Florida, and it was a special drink that they gave the Gators of University of Florida um, for after they competed, and then they marketed and called it Gatorade. All right, so how do one of these solutions form? Well, this process is called solvation. Uh-oh. We call this process solvation, the interaction between a solvent and a solute. Okay, and it's also called hydration when the solvation. It's when solvation with the solvent of water. All right, now there's some energy changes involved here, so that when things dissolve, energy will actually travel in one direction or the other. Okay, uh, if we are breaking the attractive forces that hold molecules together, or not hold molecules, hold ions together, it is going to absorb energy, and the process is endothermic. Okay, but then if we make the attractive forces, okay, attractive forces to other things, okay, then it's going to release energy, and the process is endothermic. Both of these processes occur during solvation. Okay, so what do you think happens when sodium hydroxide and ammonium nitrate dissolve? Well, I'll give you an example of both of these in class. Um, so we will find out, or it's going to be a spoiler alert here. Uh, so take a pause for a sec, and okay, so pause for about 5 seconds, and then fast forward another 10 seconds if you don't want to see what the answers are. All right. Uh, well, hope you fast forward longer. NaOH gets hot, NH4NO3 gets cold, and this would be exothermic and this would be endothermic, and we'll show those in class. Okay, which brings us to solubility and how do things dissolve. The definition of solubility, it's not just the ability to dissolve, it is to how much they can dissolve. It's the amount of solute that will dissolve in a specific amount of solvent under given conditions of temperature and pressure. All right, so how much is dissolved under certain conditions of temperature and pressure? You kind of give us back to what is the nature of a soluble solvent. Now, we know that likes dissolve likes. In other words, which means polar solvents will dissolve polar or ionic solutes, and nonpolar solvents will dissolve nonpolar solutes. Okay, so oils will dissolve in other oils, and ionic solutions, salts and acids, will dissolve in water. Okay, now we have the effects on the solubility of various things, like for instance, temperature. If it is a solid in a liquid, the solubility will increase with an increase in temperature. Okay, now think about this. If the temperature is the average kinetic energy of a molecule, okay, molecules are moving faster, molecules move faster with increased temperature. Now, if the molecules are moving faster with an increase in temperature, that means that they are going to be colliding with the solids more and causing those solids to break up and become ions as they get into the liquid. Now, the converse is true with gases in liquids. Solubility of gases will actually decrease with an increase in temperature because the gases already have, if it's a gas and they're already moving faster, generally faster than the liquid, or they will move faster than the liquid. And if we increase the temperatures, that means the gases will, the gas molecules will find each other faster, and they will form their bubbles, and they will evolve from the liquid. Okay, and from this we have our solubility graphs that we need to see, I need you guys to look at and know how they work. So I'll show you that here in a second. All right, here's a solubility graph, and here's what it looks like. So you can tell that this is end of the period. This is the amount of grams dissolved for every 100 grams of water at various temperatures. So you can see in most of these graphs that the volume goes up as we increase the temperature. However, on some of them, for example, salt doesn't change as we increase the temperature. And terbium sulfate is actually interesting, and it's a counterexample. It actually decreases as the temperature increases. Why do you think this would happen?